Okay guys, the next unit we're going to look at is the units on infinite series. So just to give you a little preview of where we're headed, we have this unit here, and then our final unit once we're done with infinite series will be calculus of parametric and polar functions. This is really a pretty short unit, and we're just going to take what we've learned so far and apply it to those two types of functions. It's not going to be very complex or difficult. This unit we're about to start, an infinite series, is the moneymaker in the BC course. Okay, to me, infinite series is what makes the biggest difference between AB and BC. It seems that the AP and the College Board feel the same way. They are going to make sure that those that do not understand infinite series very well are going to have a hard time getting the 5 on the exam. So we want to be very sharp and very motivated this unit. We're almost to the finish, but this is the unit that's going to make or break us as BC students. So this first video is going to be pretty short, and so just give us some fundamentals for the things we're going to start to see in this unit. So I want you to learn the definition and notation of a sequence, and then some of the notations and other expressions that you're going to see used quite a bit, and we need to become comfortable with those pretty fast. So let's start off with what is a sequence. We've studied functions for a year and a half now, at least together. We know that functions take in inputs and spit out one output for every input. A sequence is a type of function, but you only input natural numbers into the formula, okay, into the function. So only 1, 2, 3, 4, 5, 6, 7, etc. No negatives. Sometimes 0 is allowed depending on the situation, but in general, number of sequences have whole number inputs. Okay, so here's an example of a sequence generator. Okay, we use the notation a sub n. N tells us instead of x, and we could just as easily write a of n. Okay, but I'm just showing you what's traditionally done. They use a subscript. A sub n is our formula for our sequence, and is defined, and sometimes not defined with a formula, but in general it will be, as n over n plus 1. Okay, and this is the function you're going to input your whole numbers into. Okay, it says up here, if this formula is a function whose domain is only natural numbers, here it says let's include 0, then it generates a sequence. And we sometimes refer to this formula as the nth term of the sequence. Okay, so down here we're going to expand the sequence to show you what it looks like. I have drawn set builder notation around the a sub n to say I'm saying now the set of a sub n's looks like this. Okay, it's a never-ending sequence because I can never run out of natural numbers. If we start with 0 as our first n value, then we'll have 0, then we'll have 1 over 1 plus 2, which is a half, and then we'll have 2 over 2 plus 1, which is 2/3, 3 over 4, etc. So we put the ellipsis to say that this goes on, and then we're generally going to write another comma, and we're going to say the nth term looks like n over n plus 1. We put another comma, and then we put ellipsis after that to symbolize that this sequence goes on without end. Okay, so taking a formula, expanding it into 3 or 4 of the first terms, followed by an ellipsis. Okay, we'll be doing this quite a bit to be used to seeing kind of what numbers come out of the sequence, what do they look like they're headed towards, etc. Okay, now some notational features here that are going to pop up. Let's expand this guy here and see what we get. And let's start this one at 0 also. So if we have negative 1 to the 0, that's going to become a 1. 0 plus 1, that's 1, and 3 to the 0 is also 1. So our first entry, our first output is 1. Then when n is 1, you're going to get to negative 2 over 3. When n is 2, negative 1 squared is a positive. 2 plus 1 is 3. So I have 3 over 3 squared, that's 3/9 or 1/3. Let's do one more. Input a 3, this is going to be a negative. I've got 4 over 27. So negative 4/27. And once again, we're going to put the comma, we're going to put the ellipsis, and then we're going to put another comma, and we're going to write out the formula for the nth term. Put another comma, followed by another ellipsis. Now, what we wanted you to see in this example was that the signs between consecutive terms of the sequence alternate between positive and negatives. Okay, positive, negative, and this is going to go on forever. And the feature of the formula that does that is this right here. Okay, for lack of a better term, we're going to call this the flipper. That's not really what it's called. I don't know if it has a name or not, but this is what you will need in your formulas if you want the signs to alternate between positive and negatives in consecutive terms. Okay, and so this can be a negative 1 to the n. It can be a negative 1 to the n minus 1. Or a negative 1 to the n plus 1. Okay, so it'll be different. It might take different forms, but negative 1 to a power, as long as those powers switch between evens and odds, will flip the sign of your consecutive terms in a sequence. That's going to come up quite a bit in this unit. So I want to show you that here. Okay, we're also going to have to get used to expressing terms of a sequence in terms of previous terms or following terms, successive terms. Okay, so here's an example of a sequence that's defined in terms of the two terms before the current term. So it says here the nth term is equal to the n minus 1 term, that's the term right before this one, plus the term 2 terms before this one. So in other words, I can't just start in the middle of the sequence and start listing off terms like I could over here with this one. If I needed the 100th term of this sequence, I would just plug in 100 in for n and be good. Over here, I can't do that. I actually have to list out the terms from the beginning if I want the 20th term or the 50th term. Okay, this is called a recursively defined sequence. That's not really that important to know, but I'm just giving it to you. It means you need the previous, at least the previous one, sometimes more, terms to keep expanding terms in the sequence. So recursively defined sequence. This one's actually pretty famous. You might recognize it once we start writing out some terms. And there are other famous ones besides this one that you may have seen in your mathematical past. Okay, so let's go ahead. They give you the first two terms, which is necessary. Otherwise, we wouldn't be able to start anywhere because I need the previous two terms to get to the next one. So a sub 0 is 1, a sub 1 is 1. Now, how do we get a sub 2? A sub 2 is a sub 2 minus 1 plus a sub 2 minus 2, meaning it's a sub 1, which is 1, plus a sub 0, which is 1. So the next term is 2. And we're going to continue with that pattern all the way down. To get the next term in the sequence, you just add the 2 before it. Okay? So to get this next guy, I add 2 and 1, I get 3. To get the next one, I'll add 2 and 3, and I'll get 5. To get the next one, I'll add 3 and 5, I'll get 8. And this goes on forever, dot, 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 comma, and again I'll say, what? A sub n minus 1 plus a sub n minus 2. That's the nth term of this sequence. Comma, dot, dot, dot. Okay? And if you haven't recognized it yet, this is also called the Fibonacci sequence, which comes up all over the place in mathematics. You could probably teach a whole semester on the Fibonacci sequence and places where it pops up. We're not going to do that here, but I just wanted to show that as an example of a sequence that's defined recursively, meaning you need previous terms to come up with the next terms, but more importantly, how do you express terms in terms of other terms of the sequence? That's how you do it there. We'll do this a lot, n minus 1, n minus 2, etc. Okay, this next example right here is a special type of sequence that will also pop up. I have 1/4 times 2 to the n, and let's let n start at 0 once again. So if n is 0, I'll have 1 times a fourth. And if n is 1, I'll have, that's a comma there, I'm sorry, 2 times a fourth, which is a half. And if n is 2, I'll have 4 times a fourth, which is 1. If n is 3, I'll have 8 times the fourth, which is 2. And if I'm sharp, I'll have observed that I am doubling the previous term each time we go here. So I'll have 4, I'll have 8, I'll have 16, dot, dot, dot. And comma 1/4 times 2 to the n, comma, dot, dot, dot. Okay? This type of sequence is called a geometric sequence. It's one in which if I take two terms in a row and divide them, they'll always have the same ratio. So let me show you what I'm talking about here real quick after I write this down. Okay, if I take 8 and 16, okay, and divide 16 by 8, I'll get 2. If I take 8 divided by 4, I get 2. If I take 4 divided by 2, I get 2. If I take 2 divided by 1, I get 2. And this goes on all the way down. If I do the nth term divided by the n minus first term, I always get the same number, the same ratio, and that's what makes it a geometric sequence. We'll see this come up again not too far into the future here. Okay, now here's a symbol that we may or may not have seen before, an exclamation point. Okay, exclamation point. It's called, let's put an exclamation point after a 4. It's not an enthusiastic 4. Here's what it means to do. Okay, it means take that number, and now I want you to multiply by all of the whole numbers less than that number. Okay, so 4 with the exclamation point means 4 times 3 times 2, and if I want to write the times 1, I can. Doesn't really matter. But the symbol is called the factorial symbol. Okay, it's telling us multiply by the whole numbers less than, I should say the natural numbers, less than that number. So 4 factorial ends up being 24. And believe it or not, the factorial numbers are going to be very important in this unit. They can come up a lot. So if I'm writing out numbers in this sequence, okay, do I want to start with 0? Well, I could, and this is kind of a good place to talk about this. You may want to ask about this later, but 0 factorial is kind of the rule breaker on this little rule here, this little definition. Okay, by definition, and this is kind of like when we say 2 to the 0 equals 1, and you say, well, that doesn't make any sense if you look at it symbolically. Like if I think of this in terms of exponents, there's no way I would think that 2 to the 0 would be 1. But it has to fit all of our other rules and all of our other definitions. It can't just stick out like a sore thumb and not make sense. So it has to fit in. And so that's how we define numbers to the 0 power, except for 0 to the 0 power. Same thing here with the 0 factorial. This symbol has to fit all of our definitions and all of our rules. And I don't want to really go into it here, but 0 factorial equals 1. And that's something you just have to wrap your brain around and accept for now. Okay, we'll talk about it later maybe. So if I'm going to do the first few terms of this sequence, I have 0 factorial, 1, over 0 plus 1 factorial, which is also 1. So 1 over 1 is 1. Now, 1 factorial is 1. 1 plus 1 is 2. 2 factorial is 2. So I have 1 divided by 2, 1/2. 2 factorial, I would have 2 times 1. Here I would have 3 factorial, which is 3 times 2 times 1. So I have 2. Wait a minute. I think I can do this a little bit easier, can't I? That would have been 2 times 1 divided by 3 times 2 times 1. So those and those would cancel, and I'm only left with the n in the bottom, 1/3. Okay, so it looks like I can maybe give some shortcuts sometimes with sequences. In this case, dot, 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 I may not have to write this symbol. I could just write 1 over what? 1 over n. Interesting. Because the other parts cancel it off. Okay. In fact, let's just take a look at this more formally. I guess I could say, well, wait a minute. I know what n factorial means. It means take n and multiply by all the whole numbers less than it. And n plus 1 factorial, I guess, would mean take n plus 1 and start multiplying by the whole numbers less than n plus 1. Well, what's the next one in the chain? The next one would be n. And then we do n minus 1 and n minus 2. But hey, wait a minute. That's n factorial. Okay, and so those do cancel out, and I'm left with 1 over, looks like I was wrong, it's not 1 over n, it's 1 over n plus 1. So sometimes I need to be careful with what I do when I'm looking at sequences. I forgot I started at 0, not at 1. Okay, so there we go. So the factorial symbol will come up quite a bit. The flipper comes up quite a bit, and talking about terms in terms of terms before terms comes up quite a bit. Wow. All right, what else do we got here? All right, let's go backwards and see if we can do this. It says write a formula for this sequence of numbers. So in other words, what is the general rule here for the nth term? Okay, that's what we got to try to figure out here. Well, what's happening here in the numerator, what's happening in the denominator, and also what's happening as far as the signs go. Looks like I'm alternating signs. Positive, negative, positive, negative, positive. So I'm going to need a flipper, right? How do we get a flipper? Well, we use -1 to a power. I have to decide what the exponent's going to be, which means I also need to decide where are we starting in the sequence. Okay? So the first term is going to be positive, so I'm going to put an n here. And that means that I need to start at n equals 0 in order for this to be a positive. If I put a +1, I could make this the first term instead of the 0 term. So this will be the 1 term, this will be the 2 term, etc., etc., etc. Okay, now what's happening here? Well, the denominator looks like it's times 5 each time, right? 5 times 5 is 25. 25 times 5 is 125, etc. So that's 5 to a power. And let's see, I started with 5 to the first. This is 5 to the second. This is 5 to the third, etc. So I need 5 to the n plus 1, right? Because I'm starting when n is 0. And what's happening in the numerator here? 3, 4, 5, 6, 7. Those numbers just go up by 1. That's not too hard to come up with here. And the first one is 0. So I'm going to go, I think, with n plus 3 for my numerator. Let's see if it matches here. Okay, when n is 0, that's going to be a positive 1. 3 over 5 to the first. When n is 2, I've got 4 over 5 squared, and it's going to be a -1 in front. So I think we've got it. Now, if you had chosen n to start at 1, then your formula would be a little bit different. Okay, it wouldn't be drastically different. It would look like this. First of all, your flipper would have to have a different exponent, either n minus 1 or n plus 1. Now you would start not at n plus 3, but at n plus 2, and your denominator would be 5 to the n instead of 5 to the n plus 1. Okay, so your starting point you may have to define in your work. The problem may tell you where to begin it, but the formulas could look slightly different if you start at 0 versus starting at 1. Okay, even numbers are pretty easy to generate. Even numbers are numbers that are divisible by 2 evenly. So how do I guarantee numbers even? Well, I take my n and I multiply it by 2. That'll guarantee me that I get even outputs only. Okay, now do I like this for this sequence? Well, I do like it if n starts at 1, right? If n starts at 1, then we're good. If n starts at 0, I would want something else. Okay, so a sub n equals 2n works for this one. If n starts at 0, I would want slightly different expression. I would want what? I want the first term to be a 2, so I think I would want, I still want everything to be even, so I need the 2 in front, and I would go what? N plus 1? Would that do it? So 0 times 2 is 2. I have to put a 1 in. 1 times 1 plus 1 is 2. 2 times 2 is 4, so that would work there. Okay, so even numbers. 2 to the n, or 2 times something. Now what about odds? Well, what makes a number odd? Well, it's 1 more than an even, right? If I have an even number and I add 1, or if I subtract 1, I will always get an odd. So one of these two expressions you're going to use more than you think, probably, to create odd numbers. and it all depends on where do we start counting. Does n start at 1 or does n start at 0? Okay, this is if n starts at where? 1. If n starts at 1, we'll use 2n minus 1. And if n starts at 0, we'll want 2n plus 1. So the evens and the odds come up quite a bit. We have the flipper. We have the factorial. All right, now, one fast definition, and we'll be done with the preliminaries here. A sequence of numbers. Okay, what does it do in the long run, right? The farther you go down the list, what do the numbers start to do? That's a big question in this unit, okay? If the numbers in the sequence start to get closer and closer and closer to a certain value, in other words, if the limit as n goes to infinity of your sequence, okay, equals a number, gets closer to a number, then we say the sequence converges. Okay. Otherwise, we would say the sequence diverges. Just like we talked about with what we say, improper integrals, right? If the value was finite, we said the integral converged. If the value came out to be infinite, then we said that the integral diverged. Same kind of principle here. Let's go back and grab some sequences here. Okay, here's one. Let's copy that one. Boom, boom, boom. And let's copy one other one and take a look about whether or not these sequences are going to converge or diverge here. Okay, we'll grab this guy with the factorials. Okay, now we already wrote out some terms of these two sequences, and you may still have those written down, visible to you. That's cool. But if we just take a look here, what is the limit? The limit as n goes to infinity of this sequence. If I remember correctly, it started off with 1/4, 1/2, 1, 2, 4, 8, 16. So those numbers kept getting larger and larger and larger, and if I look at this, 2 to the infinity is a really big number. I cut it divided by 4, it's still going to be pretty huge. So this limit heads towards infinity, and that's not a finite value, so this sequence, I would say, diverges. The terms of the sequence, the farther you go down, do not approach a finite value. Here, if I remember correctly, we simplified this to be 1 over n plus 1. And your terms look like 1 over 1, 1 over 2, 1 over 3, 1 over 4, etc., etc. Those numbers we're going to get smaller and smaller and smaller, closer to 0. And we can show that with the limit as n approaches infinity of 1 over n plus 1. That does equal 0, and so this sequence converges. Okay, so your next video will start to look into what is a series, and more specifically, what is an infinite series, and you're going to see a lot of these principles pop up in that video. Making odd numbers, making even numbers, making terms flip between positive and negative, and we're going to be talking about this convergence and divergence issue quite a bit. Okay, no requirements on this video, but you'll see some of the next one.